Hi, this is question 9 from May 2015, paper 2, time zone 2, I think. And we'll have a quick look at the question itself, which is here. A machine manufactures a large number of nails. The length L millimeters of a nail is normally distributed, where L is distributed normally. This is what this means. L is distributed normally with a mean of 50 and a variance of sigma squared. That's what that symbol there means. Sigma being the standard deviation and variance being standard deviation square. And then part A is find the probability. Okay, so I've actually done this one before in a tutorial, so I'm just going to very briefly recapture what I did in that tutorial and move on. So I guess the first thing to do is what I tend to do is I tend to draw a little picture of what I know. So this is question 9. Oops, sorry, I'll go to a different color. And what I know is I tend to draw a little picture of my normal distribution, pop in what I do know, 50, and it's got a standard deviation of sigma. So the best I can do really is say that this bit here would be 50 plus sigma. I'm just going to go all the way down here and call it plus sigma, but it means 50 plus sigma. This bit here, 2 standard deviations away from the mean, so that would be plus 2 sigma. And on the other side, same distance away, would be 50 minus sigma, which I'm just going to write like that. Okay, I could keep going, but that'll do for the time being because I know what the question is. The question is find the probability of 50 minus sigma less than L less than 50 plus 2 sigma. So the way to read these kinds of statements is that L is between this value and this value. And it looks complex, but it actually isn't. It's basically saying find the probability that the length of the nail is 1 standard deviation to the left or any nail that is at least 1 standard deviation away to the left and up to 2 standard deviations away from the right. That's basically how to look at that. Okay, so we are looking at, so for part A, we're looking for the probability, 1 standard deviation to the left, 2 standard deviations to the right. So as a little picture, we're really saying, with my little bell curve here, and I'll use colors just so we can sort of see a little bit better. 2 standard deviations to the right, 1 standard deviation to the left. We don't know what the standard deviation is yet, but we're trying to find this, remembering that that is the probability there, okay? So it looks complicated, but it's not too bad. What we need to recognize is that we have this thing called the standard normal distribution. And the standard normal distribution simply said, or two dots there for the eye, simply says that if we standardize to a mean of 0 and a standard deviation of 1, for a normal distribution, we'll get the same probability. So that should be a straight line. We'll get the same probabilities, i.e. the area under the curve will be the same. But in this case, we will have a standard deviation of 0. Sorry, a mean of 0 and a standard deviation of 1, which means that 2 standard deviations away from 0 is 0 plus 2, and 1 standard deviation to the left will be 0 minus 1, and that's the same area, okay? So what I've drawn here represents the probability of Z being between 2 and minus 1. And note that I use Z instead of X, or L in the case of the question context, because Z is used to describe a standard normal distribution with a very specific circumstance of a mean of 0 and a standard deviation of 1. But do note, though, that the area in green here is the same as the area in green here. Okay, so the probabilities are the same. And because they're the same, we can simply use our GDC to complete this question. So that is equal to, and now I'm going to switch to my GDC, and I'll just clear this screen. So we start up a new document. I won't save that. Add a new calculator in, and I'm going to go to menu, probability, distributions. So menu 5, and then we're looking for a normal CDF, which is a cumulative frequency. So normal CDF. The lower bound we will use as -1. The upper bound is 2, so that's the Z minimum value and the Z maximum value. Leave the mean, which is what mu is, as 0. Leave sigma as 1, which is what the standard deviation is, because we're looking at the standard normal distribution. Click on OK, and we have 0.818595. So that's equal to 0.819 to 3 significant figures. Okay, so that, because that's the probability under the curve for the standard distribution, it's also the probability under the curve for our original question here. So it's the same as that. Okay, so that's basically part A done. Okay, part B, the probability that the length of a nail is less than 553.92 millimeters is 0.975. And we have to show that sigma is equal to 2.00 to 3 significant flat. Okay, so it's not enough just to substitute values in and kind of solve it that way. We really need to work out what sigma is for a proper proof. Okay, so you're not going to see this, but I'm going to write some facts down while I've got the screen in front of me. So what we have is that the probability that the length of the nail is less than 53.92 is 0.975. Now you can see that on the screen. Okay, cool. What we're going to do now is we are going to use a same sort of magic trick really. We're going to work with the standard normal distribution, and then we're going to bring back the standard normal distribution to answer the question with the regular normal distribution here, or the given normal distribution. Okay, so what is the value of Z? So if the probability that Z is less than some value little z, I could have used n or something like that, but we tend to use Z, is 0.975. Graphically, what I'm trying to do is I've got my standard bell curve here, my standard normal distribution, mean of 0, and I've got some value probably up here somewhere, which I'm calling little z, and I'm saying that the area under the curve there, remember that probability is area under the curve, is 0.975, and I'm asking myself, what is that value of z? And as usual, our GDC will help us do that work. So menu, probability again, this time 3 for inverse normal. The area, remember the probability is the area, so the area is 0.975. Keep mu and sigma the same, click on OK, and I've got 1.96 to 3 significant figures. Okay, but we're actually going to use 95996 in our calculations whenever we can. So that's the Z value. So who cares? Why do we do the Z value? We do the Z value because there is a relationship between Z and X, or in our case, L. Okay, and the relationship is that in your formula booklet, it looks like this: X minus mu over sigma. In other words, the standard normal value is given by the score, or the X value, minus the mean of the normal distribution divided by the standard deviation of the normal distribution. So these three things come from our, oh, you can't see what I'm writing, beg your pardon, sorry. I can't remember where I was drawing from, so forgive me for repeating what I've got here. So I worked out Z equals 1.96 to three significant figures. I've just written that down. And then what I said next over here is that the value of the standard normal distribution can be calculated by taking these three values from the given normal distribution. So the X value, the mean, and the standard deviation. That's the link between the two graphs. So again, we've got two graphs going on here. We've got the given normal distribution, mean of 50, and now we've worked out that we're going to work out that sigma is equal to 2 in a second. And we've got the standard normal distribution where we already know the mean and the standard deviation, like so, because we know that the area under the curve will be equivalent for a given range. Okay, so for this given range of 0.975, the Z value is 1.96. And the beauty of it is that I can now substitute 1.96 for Z. I can substitute, say, L for the value we're looking for. 50. Oh, sorry, not L. Pardon. We're told that the question tells us that it's 53.92 is the value of L. Mu is 50, and sigma we don't know. Now, the next thing we're going to do is a bit of a shufti. So we multiply both sides by sigma. That'll bring sigma up to here and cancel it from here. Divide both sides by 1.96. That'll cancel 1.96 there and have 1.96 here. Ultimately, it means that it's swapped position. So I've got 3.92. That's 53.92 minus 50 over 1.96. That's another GDC calculation. So we've got 3.92 divided by 1, or I won't by 1.96 because if I can use the most accurate answer I've got, it's better. So I'm going to use control ANS like that. So 3.92 divided by ANS, and that gives me 2.00004, which equals 2.000 to three significant figures. And that is what we were required to demonstrate. Oh, sorry, I haven't switched over again. So that equals 2.0004, which is 2.00 to three significant figures, and the QED says thus it is demonstrated, thus it is shown. Okay, so that's part B done. Flicking to the next page. The next part, part C, which you can't quite see on the page there we go. The next part says, a nail is chosen at random. The probability that it is a large nail is 0.75. Find the value of T. Okay, so let's visualize this first. So we've got a nail chosen at random. I'll switch back so I don't forget this time. So a nail is chosen at random. Find the probability that, and we're told the probability that it is a large nail is 0.75. So we've got this thing here. We've got it normally distributed. We've got a mean of 50, like so. And the probability that it is at least T millimeters is 0.75. It's called a large nail. So it's going to be over half. And that means that T is going to be somewhere along here. We don't know what it is. So it's this bit here. Again, I'll color code it so that it stands out. This bit here is going to be 0.75. Yeah? Now, if we know our probability, which we do, we should know that if all of that area is 0.75, then all of this area is 0.25 because they both have to add up to 1. Okay, so contextually putting it together, we can say that, because we're looking for the value of t, right? So we're given that the probability of x greater than or equal to t is equal to 0.75, which is the same as the probability of x less than t being 0.25. Okay? It must be. Look at the diagram there. You can see what I mean. This is 0.25. Cool. So now we can use our GDC again to figure what that is. So go to menu, go to probability, go to distributions, and we're going to, yes, use inverse normal to put in the area. Oops, not 0.75, 0.25. Put in the mean of 50, and this time we can put in sigma being 2 because we worked that out in part B, and we find out that it's 48.651. So from the GDC, T is equal to 48.7 millimeters. Cool. So now we've got a value for what makes it. So a large nail is 48.7 millimeters or bigger. So on my screen, that's what I've got there. Okay, T is equal to 48.7 millimeters to 3 significant figures. Part D is worth 8 marks, so you'd expect there to be a little bit of work there. It's not too bad. It's not that hard to do as long as you know what you're doing. That's the tricky bit. So part D. I guess what makes part D tricky is that it's a special kind of probability question, and that's kind of hidden. A nail is chosen at random from the large nails. Find the probability that the length of this nail is less than 50.1 millimeters. Now, what's hidden there is that this is actually a conditional probability problem. Because if you think about it, this part here means that all of the nails have been sorted into 2 piles, all the large nails and then the rest of them. Okay, so that means that the probability is actually finding the probability that the length of the nail is 50.1 millimeters or less than that actually, given that it is a large nail. Let's have a look at what that means in probability language. So part D, part 1. The probability of A given B, where A is the event that the length is less than or equal to 50.1. I should say less than actually, not that it makes a difference with the calculations that we're doing. Less than 50.1. And B is the probability that the length is greater than or equal to 48.7, the smallest of the large nails, the smallest length of the large nails. Okay, so that's what A and B are. So what we have is the probability of A given B is the probability of A and B over the probability of B. That's just our standard definition of conditional probability. But what does that mean? It means that it's the probability that the length is between 48.7 and 50.1. Okay, if you kind of read it backwards, you can see L is greater than 48.7, greater than or equal to. It really makes no difference. 48.7, and there it is there. So it's just written backwards, and L is less than 50.1. L is less than 50.1. over the probability of B, which is the probability of L less than 50.1. 48.7, sorry, probability of B. Like so. Okay, so that's that. Now that's equal to, well, let me do the easy bit first. We're told that the probability of a nail being a large nail, we were told in part C, the probability of a nail being a large one was 0.75. So we don't need to do any calculations there. We can just go straight to 0.75. But the probability of the numerator there needs to be worked out using a GDC. So back I go. And what I'm going to do is I'm going to copy this value here. So you can go Control C and copy. And then when I go to my menu and go to probability and go to distributions, I'm going to go to normal CDF. And I'm going to replace the lower bound, which by default is negative infinity. And I'm going to use this little arrow here, and then I'm going to paste, click into it and paste. And that's the actual lower bound as opposed to 48.7, which would be a little bit rounded. So we try to use our as many decimal places in our calculations as we can. Upper bound is nice and easy. It's 50.1, like so. Mu is 50, and sigma is 2. Okay, and I get 0.269939. So approximately 0.270, but I would certainly use 69939 in my calculations. So I just need to take that. Now I'm going to type in A and S here, but you can just go Control minus again. Answer divided by 0.75, and I get 0.359919. So that's equal to 0.360, to three significant figures. So that's the probability of picking out a nail that's less than 50.1 millimeters, given that it is one of the large nails. And that kind of makes sense. About 36% chance of getting a nail. Looks all right to me. Okay, so that's part D, part 1. That's worth 4 marks, I think. Part D, part 2 takes a little bit of a turn. Let's have a look at the question. Part D, part 2, 10 nails are chosen at random from the large nails. Find the probability that at least 2 nails have a length that is less than 50.1. So again, chosen from the large nails. So we've already got that conditional probability again. But in part 1, we've already worked out what that probability is. So either a nail is less than 50.1 millimeters or it isn't. Yep, just one of 2 possibilities. So that's when we can talk about a binomial distribution. So in a binomial distribution, we say that X is distributed binomially, and then we put in the number of trials and the probability of success. So in this case, we can say length is distributed binomially, 10 trials, with a probability of 0.360, like so. So what we're asked to do is to work out the probability that at least 2 nails have a length that is less than 50.1. At least 2 nails. That at least should always give you pause to think. What does it mean algebraically? It means that we're looking for the probability that L is bigger than, at least, that's bigger than or equal to 2, like so, which means that we're looking at 1 minus the probability of X less than 2. In other words, 0 or 1. 1 minus because I've used a complement. So if I subtract X less than 2 away from 1, I'll get the probability of L greater than or equal to 2. Okay, which equals 1 minus, let's work that out. So we're going to use our GDC again. I'm going to use, this is my probability, so I'm going to copy it. Hopefully that copied it. Mine menu, probability, distributions, and we're going to go down this time to B, which is binomial CDF. So click on that. Number of trials, 10. Probability of success, click on the arrow and paste it in, all those decimal places. The lower bound is going to be 0, and the upper bound is not 2, but 1, because it's less than 2, not less than or equal to. Click on OK. And I've got, whoops, that didn't work. Let's try that again. I don't think the cursor was blinking in the right spot. So probability, distributions. I'm just going to hit B, and they'll get me to binomial CDF. 10 trials, probability of success is 0.35999, blah, blah, blah. Lower bound of 0, upper bound of 1, and click on OK. And there I've got 0.076455. So 0.0765, which equals, and I'm going to go 1 minus answer here. I'm just writing this down as I go along, but you'll see it in a second, which equals 0.924 to 3 significant figures. So there's a 92.4% chance of getting a nail, of there being at least 2 nails, which sort of seems reasonable to me. So that's what it looks like here in the question. 92.4% chance of being right. Kind of feels right to me. Just to confirm, here's the mark scheme. And we've got 0.819 as our value, as the value it had. And we got 0.819. We got Z equals 1.96, and then through to sigma equaling 2. And you'll see in the mark scheme, pretty similar. With C, we got T equal 48.7. We got 48.7, lovely. With D, 0.35999 or 0.360, we got 0.360. And lastly, they got 0.924, and we got 0.924. So that all works out. But I want you to note that at the very top there, it says there may be slight difference in answers depending on which values candidates carry through in subsequent parts. In particular, there are a number of ways of doing D, except answers that are consistent with their working. So as you can see, by what I did is all the way through, I wrote down 3 significant figures in most places, but calculated with the full value in the calculator by using copy and paste. And that's what allowed me to have consistent answers with the mark scheme. But if I'd used 3 significant figures in my calculations all the way through, I would have ended up, for example, with a probability of 0.349 here, which is quite different from 0.360, and a final probability of 0.913. Now, I can't tell you for sure that a marker would give you full marks for that. They probably should do, but they might not. So where possible, copy and paste your values through to make them as accurate as possible. Okay, that's it for this particular question. I'm going to do a follow-up with question 10 from the same paper in a separate video.